So in today's video, we're going to go ahead and delve into how we can actually correlate a function to its antiderivative graphically, right? And I mean, we know how, definite integrals of a function, we kind of can interpret it graphically as sort of the area under the curve over a particular defined region. But when we looked, in the previous videos at these different examples, using the fundamental theorem of calculus, right, we determined that the definite integral kind of gives us the antiderivative of a function, right? Then this provides a new sort of interpretation of what the integral actually is. Instead of just being the area under the curve, we can kind of think about it as the antiderivative. And so suppose we have a function g of x, and we define that as the definite integral from a to x of f of t dt, right? Then this directly implies that the derivative of g, so g prime of x, is in fact equal to f of x. So we replace, this dummy variable t right over here, we replace it with an x when we take the derivative of g, right? And so because of that, if we want to kind of take a look at the graph of some arbitrary function f, so suppose that this right over here is the graph of f of x, we can just rewrite f as being equal to g prime, right? Because I mean, that just comes from this relation right over here. F and g prime are essentially equivalent. And so whenever we have a graph of f, we can immediately kind of think about the graph of g as a result. And so let's go ahead and kind of interpret a couple of different things about g. Let's think about how the function g of x may look because of, or given the graph of f. And so we can replace, like I said, this f with g prime. And so essentially this is just going back to our differential calculus playlist where we were graphically correlating, a function and its derivative and kind of interpreting function behavior using the derivative. And so let's go ahead and actually, see what we can do right over here. So first of all, we have this point right over here. Let's just take a look at it. Let's suppose we call this point, C. At this point right over here, the graph f has a local maximum, right? And we know that because we have a stationary point. We know that f prime is equal to 0, so f prime is equal to 0. And we also know that because, over here, f prime is positive, so f prime is greater than 0. And then over here, f prime is now less than 0, right? It starts to decrease. And so we're increasing, we reach our maximum where f prime is equal to 0, and then we start decreasing again. And so what does that tell us about the graph of g? Well, we know that f prime is equal to 0, and we know that f is equal to g, and so we have that f prime is equal to 0, but what is f prime equal to? We know that f is equal to g, or f is equal to g prime, so this is just g prime prime, right? G double prime. It's the second derivative of g, right? And so when g double prime is equal to 0, that tells us right over here that g has an inflection point, right? A point of inflection. And so essentially we're just able to use the fact that f has a stationary point in order to determine, or a stationary point and a local maximum, to determine the fact that g will have an inflection point. And we can use that same logic for this point right over here. Suppose we call this point b, and we again have f prime is equal to 0, f prime, which is equal to g double prime, is equal to 0. We also have the fact that f prime changes signs over here, so initially f prime is negative because f is decreasing. Okay, can this stop? There we go. And then over here we have f prime is now positive, right? F prime is greater than 0, and so we also have an inflection point. So inflection point at C, and then again, and at B, right? And so we have that right over there. We were able to determine that g is going to have certain inflection points. What else can we say about this function? Well, let's take a look at this interval right over here, from -1 off to -infinity. And so we know that for x is a member of the interval, let's say the open interval from -infinity to -1, we know that g is going to be increasing, that g is increasing. And how do we know that g is increasing? Well, that's because f is greater than 0, right? So f is positive, which tells us that g prime is positive, right? And so because f is positive over this region right over here, that immediately tells us that g is increasing, right? Increasing. And the same logic can be applied for this region right over here from 7 off to infinity. So for x is a member of, let's say, from 7 to positive infinity, the open interval, g is also, or g is going to be decreasing in this case, is decreasing, right? And that is because of the fact that f is negative. And we know that f is equal to g prime, so g prime is also negative, and hence g is decreasing. And we can analyze various different aspects of this function, or of the function g, just by looking at the graph of x. And this is just a couple of examples of things we can do. We can look at inflection points, at intervals over which your function is increasing and decreasing, concavity. The whole point is that when we have the function f, and we're given the fact that f is the antiderivative, or g is antiderivative of f, then we can immediately consider what the graph of g may actually look like. And so this is just the whole point of this video, is just to kind of illustrate how we can actually do that.